In the previous two videos, we've considered three very simple, straightforward to implement iterative techniques for solving the Poisson equation or other elliptic partial differential equations. So it's Jacobi, Gauss-Seidel, and the successive over-relaxation or SOR method. And in this video, we're going to look at an improved method known as Alternating-Direction-Implicit or the ADI method. We'll talk about the deficiencies of the previous techniques and how ADI addresses those deficiencies. Remember that we're solving elliptic partial differential equations, and remember that in elliptic partial differential equations, the solution anywhere depends on the solution everywhere instantaneously. So we need a global technique for moving information throughout the domain numerically to be faithful to the mathematical character of the elliptic partial differential equation. If you think about the point-by-point iterative techniques that we've been discussing in the previous two videos, you'll notice they are not really faithful to this elliptic character. It's because they're being implemented in a point-by-point way. So if you take a simple example, suppose we're sweeping from the left to the right. So we're sweeping through I from 1 to capital I plus 1 along constant y lines. If we had a particular boundary condition on the right boundary, you'll notice it would take capital I iterations for that boundary condition to be felt on the left boundary, because the first sweep through the grid would only be the capital I point, the one right next to the boundary, that would feel the presence of the boundary. The next iteration would be the next point and the next point. And it would actually take capital I iterations for the left boundary to feel the presence of whatever's happening at the right boundary. So the point is, these are not very elliptic-like in terms of the mathematical character of these elliptic equations. So we'd like a more elliptic-like method, a method that numerically spreads information throughout the domain, throughout the grid, in a more effective manner. If, for example, we're sweeping along lines of constant y, so again, horizontal lines in the grid, you could imagine that maybe we could solve the entire y line implicitly. So that would mean that we're solving for all the unknowns on that constant y line all together in one shot. Now that may sound familiar. That's exactly what we did when we solved the one-dimensional extended fin example using the Thomas algorithm to solve the tridiagonal system of equations that we had. So the question is, can we change the way we look at this two-dimensional problem such that we can take advantage of that more elliptic-like character of the Thomas algorithm to move information, in this case, all the way along a constant y line? And the answer, of course, is that we can. So let's go back to our Poisson equation, second-order accurate central difference approximations, and we have our 5-point stencil, so the 5 unknowns, uij, then the north, south, east, and west points that surround it. Let's look first at constant j lines, constant y lines in the grid. So we can imagine keeping on the left-hand side the 3 unknowns that are in that line. So here's our 5-point stencil. And if we're doing the jth line, then we have 3 unknowns that are on that line. These other 2s we'll put on the right-hand side and take them as known. So for now, we'll just take them from the previous nth iterate. So we now have 3 unknowns on the left-hand side. Everything else is on the right. And when we apply that to every point along that constant j line, constant y line, we now have a tridiagonal system of equations to solve, just like we did for the extended fin. So essentially, each constant j line is a one-dimensional extended fin problem that we can then solve using the Thomas algorithm to solve that entire line all in one shot. Let me make a few comments about this. If we're sweeping through the constant j line, say from bottom to top, then the point below our current line, so the ij minus 1 point, will have already been updated. So we use that updated value just like we do in Gauss-Seidel. SOR could also be incorporated into our tridiagonal solve. So you do the tridiagonal solve, then you could use SOR to accelerate the iterative process if you wish. And the reason why this is advantageous is because this approach then is more efficient in moving information back and forth across the domain. In addition, it also takes advantage of the very efficient Thomas algorithm. We said it's so efficient that in the future, even when we're solving 2 or even 3-dimensional problems, it makes sense for us to think about how can we encapsulate those 2 or 3D problems into a series of Thomas calls, because they're so efficient for these tridiagonal systems. So this gives us the motivation for how we could do that. Now let's put this all together to formulate the alternating-direction-implicit method, or the ADI method. Obviously, if we do it along constant y lines in the x direction, it makes sense to do the same thing along vertical lines, constant x lines in the grid as well. So we can move information both vertically and horizontally very efficiently, very effectively throughout the domain. So that gives the alternating direction aspect. The implicit part is what I said before. For each Thomas call, we're solving a tridiagonal system of equations for all of the unknowns along the entire line in the grid, whether horizontal or vertical. So it's in that way that it's implicit, as opposed to Jacobi, Gauss-Seidel, and SOR. There we had explicit expressions for uij in terms of everything else. So generally speaking, having more unknowns, such as is the case in ADI, we'll have a more complicated algorithm requiring more computation per iteration, but the goal is to reduce the number of iterations sufficiently to offset that and to be faster than the point-by-point sweeping. Again, taking advantage of the fact that it's more faithful to the mathematical physical character of the problem. So here's what we would do. We would divide up each iteration into two pieces. So the first goes from n to, say, n plus a half, and then from n plus a half to n plus 1. The first half of the iteration, we would sweep along, say, lines of constant y, so horizontal lines, and then lines of constant x for the second half of the iteration. So for the first half, very similar, but not exactly the same. I'll point out the differences. We would have our I plus 1j, ij, and I minus 1j points on the left-hand side to form the tridiagonal system of equations. Everything else is on the right-hand side. Now you've noticed I've done a couple of things here. One is I have uij on both sides of the equation. I'll discuss why that is. That's physically motivated, and I'll discuss why that is in a moment. I've also subtracted a minus sigma uij from both sides of the equation, and that will be to enhance diagonal dominance. I'll talk about that aspect as well. But in any case, we now have a tridiagonal system of equations for each constant y line. So again, this is a Thomas call for each j. So let me summarize this first half iteration. So we have these tridiagonal systems to solve. We'll do them sequentially from the bottom to the top. As we said before, if a point has already been updated, then we will take advantage of that in our tridiagonal solve. So in this case, this point, the ij minus 1, is actually at the n plus a half iteration because it's already been updated in the previous y line that we solved. So that's reflected here with the superscript n plus a half versus the n for the other two terms. So let me address this splitting where I keep uij on both sides of the equation. So remember the original differential equation is partial squared u partial x squared plus partial squared u partial y squared. So the second derivatives, when we use second order accurate central differences, we'll have a minus 2 uij from both of those terms. What we're going to do is split them and keep everything having to do with the x derivatives together on one side of the equation and everything having to do with the y derivatives on the other side of the equation. So this is physically motivated. It's intended to mimic numerically the physical diffusion in the x direction, diffusion in the y direction. So again, we call that the splitting method. Remember, this is physically motivated. This is unlike the sigma uij term that I'm subtracting from both sides of the equation. This is purely for numerical reasons. This is numerically motivated in order to enhance diagonal dominance. If we look at this, we have 1 plus 1, which of course is 2. If sigma were 0, that would exactly balance the magnitude of the diagonal term, which is 2. So it's only weakly diagonally dominant. So by having a positive sigma, you can improve it so it's strongly diagonally dominant, and therefore hopefully have better iterative convergence behavior. Those two terms do cancel, so I haven't changed the equation in any way. I'm just changing the iterative properties of the method. Now once I've swept through the constant y lines, the horizontal lines in the grid, we then alternate directions and do the constant x lines. And this will be in the n plus a half to the n plus first portion of each iteration. So I'm just taking the points that were on the right-hand side, putting them on the left. Those are on the left, putting them on the right. So now on the left, I have the uij plus 1, uij, and uij minus 1. Those were on the right before. And now I have the I plus 1j, ij, and I minus 1j that were on the left. Of course, the fij term stays on the right in both cases. So again, I have a tridiagonal system, 3 unknowns on the left, that I'll solve for implicitly for each constant x line for all j along each x. Once again, if I'm sweeping from left to right, then the point ui minus 1j has already been updated, so that's reflected in its superscript n plus 1. This is done in a Gauss-Seidel sense, so we just put the new values in the two-dimensional array as we obtain them. We don't have to keep track of the n's, n plus a halfs, n plus 1s, but I'm just indicating here to emphasize the point that this value has already been updated. The acceleration parameter sigma, again, is the same, and it's on both sides of the equation. And again, it's to enhance diagonal dominance of the tridiagonal system of equations that we have to solve. You'll use the same sigma for both the constant y lines and the constant x lines. Now for our model problem, remember the model problem is the Poisson equation, second order accurate central difference approximations, Dirichlet boundary conditions all the way around, delta x is equal to delta y, and so on. So this is the model problem that we're considering as a canonical example of an elliptic PDE. For that particular model problem, we actually know what the sigma is. It's 2 times cosine of pi over r, where r is the largest of the number of points in the x direction or the number of points in the y direction. In general, for most problems, we do not know sigma, and we have to try different values of sigma. You can use this as a starting point, but this will not give you the best sigma. And in fact, this sigma may not even work for a different case. So if you change the boundary conditions from Dirichlet to Neumann or Dirichlet to Robin, then this is no longer the best value of the acceleration parameter sigma to use. Each iteration involves solving all of the constant y lines and constant x lines. So that means that every point in the grid is being updated twice per iteration, and there are capital I minus 1 plus capital J plus 1 tridiagonal solves, all of the j lines and all of the x lines. Again, they're very efficient using the Thomas algorithm, so this is a very good and a very elliptic-like algorithm. It efficiently moves information throughout the grid. Now, as you might guess, when you implement this on a computer, programming is going to be a little bit more complicated, and there's certainly significantly more computation per iteration. So that has to be matched with a significant reduction in the number of iterations for ADI as compared to Jacobi, Gauss-Seidel, or SOR. And indeed, for linear problems, that's typically the case. So the actual computational time is reduced significantly using ADI as compared to the point-by-point methods. Once again, that's because it's more faithful to the elliptic character of the Poisson equation or other elliptic equation. One additional advantage of ADI is that the boundary conditions are easier to implement in the ADI method as compared to Gauss-Seidel SOR. You remember there that when we had a non-Dirichlet boundary condition, we had to come up with a special equation that applied at the boundaries, at the corners, and so forth. We could end up with up to 9 different equations for the interior and boundaries and corners and so forth in order to update the entire domain. In the ADI method, things get a little bit simpler because now we're solving these 1D problems. We already have the Thomas algorithm that can accommodate Dirichlet, Neumann, or Robin boundary conditions at both ends, whether horizontal or vertical. So this simplifies application of the various types of boundary conditions in the ADI method. The one thing you do need to keep in mind, say for example the bottom boundary is non-Dirichlet. If it was Dirichlet, you would of course just put the values in, you would start your sweeping at j is equal to 2, it would pick up the values on the boundary when necessary, and you would sweep up accordingly. If you have a non-Dirichlet boundary condition, the values of u are not known on the boundary, they will need to be calculated and updated, so you will have to apply the ADI method along that lower boundary. If you do that, you'll notice your ui j minus 1 term will be outside the boundary, because j minus 1 then would be 0. So just as we did for those point-by-point iteration techniques, we would need to use the boundary condition to eliminate that value. But it's no different, and again, much simpler because you don't need to worry about the corners separately, they take care of themselves. In the next video, we're going to talk about the multi-grid method. The multi-grid method is really a framework, it's not a different method, it's a framework that you can wrap around these iterative techniques, whether Gauss-Seidel, ADI, for example, to accelerate their iterative convergence. They're very complex. It'll take us a few videos to discuss the multi-grid technique, but it's well worth it as the multi-grid methods can significantly accelerate whether ADI or Gauss-Seidel. We'll talk about that in the next video.